Okay, this slide is showing you the pulmonary circuits and the systemic circuits. And the purpose of the systemic circuit is to take blood to the body and give all the tissues of the body oxygenated blood, and then take away carbon dioxide from those tissues. And then the purpose of the pulmonary circuit is to oxygenate our blood and take that oxygenated blood back to the heart. So if we look at the pulmonary circuit, what we have is we start off with our pulmonary trunk, and we're taking blood away from the right ventricle. So when our right ventricle contracts, it sends blood through that pulmonary trunk, and that low oxygen blood goes through the pulmonary arteries, because these are taking blood away from the lung. And so the pulmonary arteries take the blood. Remember, we have two pulmonary arteries here. We just see one. We have the left and the right, taking them to the left and the right lungs, respectively. And so we go to the lungs and we pick up oxygen, and then we're going to go back, and we're going to go back through the pulmonary veins. So there are four pulmonary veins here. It just looks like they're one, but there's four pulmonary veins feeding into the left atrium. And this pulmonary veins are red because they're carrying high oxygen blood. So remember, in the pulmonary circuit, the vasculature is colored in a way that you wouldn't expect it to be. The arteries are blue and the veins are red. So that's kind of odd. So we take our high oxygen blood back into the left atrium, and then that blood is going to go from the left atrium through our little mitral valve. I didn't mention our pulmonary semilunar valve here. That's going to be the pulmonary semilunar valve. But here we go. Our high oxygen blood goes from the left atrium down into the left ventricle, and it has to do so through this mitral valve. And that high oxygen blood then goes through this aortic semilunar valve here into the aorta, and we start our route through the systemic circuit. So we go high oxygen blood through the aorta and out into the body, where we nourish the body, that high oxygen blood, carbon dioxide poor at this point, and we drop off our oxygen and we pick up carbon dioxide. And so on our way back to the lungs, we've got low oxygen and high carbon dioxide. And we enter back into the right atrium here through our superior vena cava and our inferior vena cava. And the inferior vena cava is draining everything below the diaphragm, and the superior vena cava is draining everything above the diaphragm. There's another blood vessel that's not on here, and that's the back of the heart, is the coronary sinus. It is also dumping low oxygen, high carbon dioxide blood into this right atrium. And that is, the coronary sinus is draining the blood from the actual myocardium itself. This white area of the heart here has to receive blood, and that's from the coronary circulation, and all the coronary veins dump their blood into the coronary sinus, and it dumps its blood here into the right atrium. And then we start over. That blood goes from the right atrium through this tricuspid valve here that's open down into the right ventricle, and out we go through this pulmonary valve, and we start our way through the pulmonary circuit. Now, if you'll notice on a heart how thick the left atrium is compared to the right ventricle, the left ventricle is compared to the right ventricle, and that's because this left ventricle has a lot of work to do when it's pumping its blood through the entire body, through the systemic circuit. It just has a lot more work than the right ventricle. This pulmonary circuit is a low pressure system, so the walls of the right ventricle are going to be much thinner. Whereas the left ventricle, when it pumps, it has to pump all the way through the body, and so this is a high pressure system. The systemic circuit is a high pressure system. Okay, now this is just a picture of the coronary circulation, the arteries and the veins. We've seen these arteries on other pictures, and so you'll need to know them on other pictures, but this is a good picture because it shows you how much longer this left coronary artery is than what you actually see it on the other pictures, because the left coronary artery and the right coronary arteries, they're coming off of the aorta, but this left coronary artery is hidden behind the pulmonary trunk, and so you can't see it, and behind this left atrium, so you can't see it until it branches into the circumflex and the anterior intraventricular. So just be aware how much longer it really is. Also, another thing to point out on this picture are the anastomoses that occur. Singular is anastomosis. An anastomosis is when blood vessels merge to form alternate pathways. So if one becomes blocked, say if it becomes blocked here, then it provides an alternate pathway for blood to go, and then that way you don't have to worry so much about, well, blocking blood flow to certain tissues. Now on this side over here, we don't have to know all of our veins, the anterior cardiac, the small cardiac, the middle cardiac, or the great cardiac veins, because I told you you didn't have to know them. However, you do have to know the coronary sinus because all of these veins drain into the coronary sinus. So all of these arteries will pierce into the myocardium, and they will service the myocardium itself. They'll give that myocardium lots of oxygen, so the myocardium can actually contract and do its job. These arteries get smaller until they become capillaries, and those capillaries will become larger until they become these veins, and all the venous blood will drain into this coronary sinus, which dumps into that right atrium. The blood flow to the myocardium itself is pulsatile because when the heart contracts, it clamps down on those capillaries and it temporarily stops blood flow to the heart, but that's how things are with the heart. So in this picture you'll see a nice healthy heart, but down here you'll see an occluded heart, a little blocked artery, and this is showing you what a bypass surgery would do. If they took a saphenous vein from the leg and they took it and they bypassed the blocked region, so blood would flow directly from the aorta down past that blocked region. So this would just be one bypass, but you've probably heard a triple bypass where you would, bypass 3 different regions, etc. This is just a different picture. Here's a very large bypass right here. So you can look up different pictures online if you'd like to. And this is a cool little link. If you just type in on Google Medline Plus surgery videos, you don't have to actually go to this exact link if you don't want to, but if you type in Medline Plus surgery videos, you'll get a list of videos a mile long, any kind of video you'd like to see. So this is the inside of a ventricle, and they've blown it full of air and there's a light in there, and this is what it would be like if the ventricle were contracting. And systole, the ventricle, where this is ventricular systole, that's contraction. So this is a papillary muscle. Here the chordae tendineae, and above here this would be either the tricuspid valve or the mitral valve. So those are the atrioventricular valves. And in the background, well, that's another papillary. Here's a papillary muscle, and there's another one. The walls, the woven walls, are the trabeculae carneae. So what the function of the chordae tendineae would be is to keep those atrioventricular valves from blowing back up into the atria. Because when the ventricles contract, they do it with great force, and they're blowing the blood, they're sending the blood up into either the aorta or the pulmonary trunk. And when they blow the blood there, they don't want the blood to go back into the atria. So we want to hold those valves closed, and that's what the function of the chordae tendineae would be. And the papillary muscles will contract, and when they contract, they're just holding these taut to hold those valves down, to keep those valves closed so the valves don't prolapse, in other words, open up into the atria and allow the blood to flow back into the atria. So that would be the function. So we have 2 different types of heart valves. We have our semilunar valves, and then we have our atrioventricular valves. And the atrioventricular valves are between the atria and the ventricles, and the semilunar valves are at the base of the great vessels, leaving the ventricles. All of the we have 4 valves total. 3 of the valves have 3 cusps. Only one of them has 2 cusps. So let's start with our semilunar valves. The semilunar valves would be the pulmonary valve and the aortic valve. The pulmonary valve is at the base of the pulmonary trunk, and the aortic valve is at the base of the aorta. And the purpose of the semilunar valves are to prevent blood from falling back into the ventricles after the ventricles contract. You'll see this on a picture here shortly. The atrioventricular valves, one of them is tricuspid. It has 3 cusps, and the other one is a bicuspid valve, has 2 cusps. The tricuspid valve is on the right side, and it's between the right atrium and the right ventricle. And the bicuspid valve is called the mitral valve. It's on the left side between the left atrium and the left ventricle. These are the valves that have the chordae tendineae. If we watch blood flow as it flows into our receiving chambers, into our atria, it's going to flow into the atria, and that pressure against the valves, these atrioventricular valves, is going to keep them open, and the blood will flow into the atria and start filling up, and then flow passively into the ventricles, and that will keep these valves open. And then as the blood flows into the atria, like I said, then it will flow right into the ventricles, and those valves will be open. It looks like the chordae tendineae are holding those valves open, but they're not. The valves are just open because there's more pressure on in the atria than there is in the ventricles. That's how valves work. Wherever there's pressure, that's what keeps them open. Now, when the blood flows down into the ventricles, when pressure starts building up in here, that starts to close these valves. When there's enough pressure, the valves will close. When the ventricles start to contract, when they're going to contract, this is what it looks like. The chordae tendineae, these papillary muscles, are going to contract and hold these chordae tendineae taut to prevent blood from being thrown back up into the atria. We don't want any prolapsing here because we don't want to pump the same amount of blood over and over again. So that's the purpose of our atrioventricular valves, to prevent blood flow back up into our atria. So there's a lot of pressure in our ventricles at this point. Now, to get these valves to open, this is our pulmonary semilunar valve, and you can't see it, but right here at the base of the aorta would come behind here in this way. At the base of the aorta would be the aortic semilunar valve, or just the plain aortic valve. To get it to open, we have to overcome the pressure. We have to provide enough pressure to open up these 3 little cusps. There's going to be blood inside these vessels already from the last ventricular contraction. Let me show you that. So when the ventricles contract, they have to have enough, this up here, when the ventricles contract, they have to contract with enough force to open up these vessels. But what you don't see here is there's already blood in here, and there has to be enough force to overcome the force that's on the other side of here. There have to be enough pressure to overcome the pressure that's already up here. So the ventricles contract with enough force to force the blood through here, and it opens up the pulmonary semilunar valve and the aortic semilunar valve, which is partially hidden here. And when the ventricles relax, then the blood pulls back down onto these cusps. See the shape of the cusps? And just hold the blood will circle back around like this. It just holds on to it like little cups. And this is when the ventricles are relaxed, and the whole cycle will start over again. So the purpose of the semilunar valves is to prevent blood flow back into the ventricles when the ventricles relax, so they don't have to pump the same unit of blood over and over again.